Next, I want to get into how we develop our model. So a bit of some methodology. The first step is we do residuals, and we've talked a bit about residuals, but here I just want to make sure that I show the equation. Residual, which I'll represent as capital R, is the log of the observation minus the log of the prediction from the GMM that we saw before. Using those residuals, we partition them using a statistical method called mixed effects analysis. And by this way, we hopefully can assign random effects towards the event bias and site bias and stuff like that. But we already hypothesized that they're path effects, so we wanted to be careful to estimate our event bias only using what I refer to as path unbiased residuals. So we only use observations within 100 kilometers, so we do this mixed effects regression where CK is kind of an overall bias. So something that we can't attribute to being an event-specific bias or a site-specific bias. The model always predicts a little higher than what the ground motion suggests. Eta E is our event term, so the event bias, and this delta Wij we've seen a couple times as the within event residual. So to illustrate what I mean by that, we have total residual versus distance, and here's our zero line. For a given earthquake, you might have observations that look like this. In this case, the observations are flat. This means that our path model that the ground motion model used is unbiased. It does a good job. It doesn't trend up. It doesn't trend down. So we can compute an event term approximately equal to the mean. That's not exactly what it is, but for demonstration purposes, we'll just call it the mean of our observation. But what happens when we have an event that there was a systematic downward trend? You can see in the dashed line that pretty much as we get to far distances, we see this higher rate of attenuation, so lower amplitudes. And this is a path effect that we see manifested in the residuals. And a traditional analysis that isn't careful with assessing these path effects would get an event term that's just the average value again. You can see that there's quite a bit of misfit at near source distances, quite a bit of misfit at long distances. This event term really only represents kind of the bias at wherever it crosses your data. It's not a good representative for the total event bias with respect to distance. It's biased with distance. These path-biased observations are going to be our close observations out to about 100 kilometers based off of visual inspection, where they're relatively flat. We don't see them bend down. We don't see them bend up. So we will only use those data to estimate our event terms.
And so do you see this in all events, this area of unbiased, common to?
Yes. So this goes way back to when I first presented how we model path effects, how we had that general shape.
Right.
For most events, the geometric spreading term is pretty okay for California. It's just the anelastic term in the path model that we're observing issues. So again, that we see effects mainly at really far distances. So that's why our residuals only trend at these far distances.
Okay.
So we estimate event terms here, and that way this represents the event bias, and then this offset is going to be mapped into site bias and path bias. Again, it's difficult to decouple things, as we'll see. So that's a pretty important thing, pretty important step that a lot of traditional mixed effects analyses won't necessarily look into, is whether or not their path is contaminating their event bias and their site bias. And the reason why that's important, just as a quick aside, the event bias, this eta E, and the site bias, eta S, are the residuals that we use to develop the site model, or the source model, which is that FE from the ground motion model, and the site model, the FS. So path can mess up the entire ground motion model if you're not careful when you're separating these effects.
Okay.
So after we separate our event bias, we then look at trends of within event residuals versus distance, lots of different plots. This is just data visualizing to come up with a path model function, essentially, that we want to use. After we do that, we compute the model, or we regress the model rather, and then we recompute residuals using that updated model, and we get new estimates for our biases and our within event residual. And we keep doing that for each until we get convergence of our bias terms, the eta E and the eta S, and also in the coefficient estimates for each subregion. And the important thing is once we get to the point where most of the path effects have been properly captured in our model, we'll do a mixed effects using all of the data. Because remember, this step only uses a subset of the near source data, but we want to use all of our data during our analysis. So we'll do everything all at once we have a better grasp on the path effects.
And are you trying to get this to 0, or are you just trying to quantify it? It's
We're
the
just,
total that you want to get to 0, right?
yes, we want this
Right.
Rij to get as close to 0 as possible, meaning these three terms, well, essentially these four terms, which would be the overall bias, the event-specific bias, site-specific bias, and then kind of any remaining randomness is generally contained in this last term. We want all of these to be as close to.
And this is when we do the ground motion models, this then goes into the sigma model and things like that, right?
Yes.
Okay. All right.
Yes.
Thank you.
And then the last step in our methodology is just to evaluate performance using a residuals analysis where we look at those uncertainty terms to see if we're improving the model, which would be dispersion calculation.
Cool.
So let's look at some data. First, let's just start with California, all of our data set. Because we just used we're using BSSA 14, the Bohr et al. 2014 ground motion model, the average residual should trend about 0. And we see for all of the data, it does. It's maybe slightly negative at far distances, but for the most part, this is what I would consider flat. So as an average, the path model is doing a pretty good job.
And this is the complete data set that you're using. You're not just NGAOS2 plus all the new data.
Yes, only magnitudes greater than 4 and within cutoff distances and other screening, but all of the data that passes our screening criteria.
Okay.
However, when we look at separation of large events and small events, we can see that large events where we only added a handful perform a lot better at far distances than small events where we added quite a lot of data. So you can see, because these bend down as a subset of all of California, that suggests that maybe there's a region or 2 or 3 that has faster attenuation than what the NGAOS2 data set had. So this would mainly be in the northern part or the eastern or the central parts of the state, because that's where essentially the new data is with respect to the model. Maybe there's some bias with respect to those regions. So we needed to essentially, we want to bring these bin means with the red dots up to 0. So to do that, we do apply the cell-specific math, essentially, which is taking our earthquake, which can be represented by this rectangle. This is the fault surface projection. And if we have sites, which are represented by triangles, we can compute the path length within each subregion. So for example, in this site 2, it's only contained within one subregion. So the path length or the weight or proportion of the path that goes through this subregion is going to be 1. The entire path is in this region. Path 3 goes through 3 subregions. So you will have path length for these 3, 0 for everything else. And the same can be true for site 1 that travels through a bunch of different subregions, where now we can quantify which subregion might be controlling the path effects. So to do that, next we separate data based off of where the majority of the path travel. So if 50% or more of the path travels through a subregion, it's plotted in each of these plots. So for example, the North Coast, we can see there's some issues at the near source, but we ignore them for now because those aren't path issues, those are different issues. But it bends down. There's a little bit of a bump up that's likely related to the Moho bounce that's been observed in Northern California. But for the most part, the trend is downward. And then we see Bay Area still downward, but less negative, and Central Coast is closer to 0. This essentially agrees with our previous observation that along the coastline, which are these provinces here, the north had the really low values for QS, so the high attenuation, that decreased as we moved south, which we're seeing here in the data. So these subregions that we've drawn capture capture what we were seeing in the QS model, also in the data. The same can also be said for the Sierra Nevada, where it bends upward, it has less attenuation. So that's also consistent with what we were expecting. And we have other subregions where the model performs pretty well. Both of these subregions already had data in NGA-West 2, so we'd expect them to be relatively unbiased, which is what we see. I'm gonna pause for a moment there.
I'm muted. Hey,
Oh.
I was talking. Do you want to take a little break, or you're good?
Oh, I'm good.
Okay, so let me try to understand these plots a little bit better, because you've got 3 different quantities plotted and on 6 different plots. So you've taken you all the residual versus distance, and you have put into each one of these plots only it's not all the same data. So out of the million of points that you had before, you look at each one and you said, okay, what region has the most, more than 50%, you said?
Yes.
Or, okay. And you put, and so one dot in the previous plot just goes into one of these 6 figures.
Yes.
Right? There's no duplication. Okay. So we've put in, okay, so which one is governed? So this tells you that the path is governed by each one of these regions. Then, and you plot the magnitude distance, you do these fits, but then you've got a color here. You've got a shading here that says path weight within subregion. Okay. Oh, okay. So you took them and you move the plot here. And then you said, hey, if it's 100%, so for example, these dark black dots, it means this is coast to coast, north coast to north coast. It doesn't cross any other region. And it makes sense for shorter distances, but as you get longer distances here, it's definitely at least 50%, but maybe it's not really governing. And so it's 51%, but you haven't plotted in another plot for the 49%, right?
Yes.
So we don't know what the rest of it is, but at least it tells me, hey, these are, okay, now I understand.
And just to build off of that, because that's a good point, a good example of why that's important is the Bay Area, where you can see at far distances, so most of the paths that kind of stay in the Bay Area are positive, whereas the others bend down, which have less weight. And we've actually looked into this, and the reason why it bends down are these are paths that are traveling north into the North Coast. So the North Coast is causing these points to be more negative, whereas the Bay Area itself is pretty okay.
How do you know it's an earthquake? It's not an earthquake in the North Coast coming to the Bay Area, or vice versa?
Or it could be vice versa, yeah. But
okay,
we've looked pretty comprehensively at these data, especially in the North Coast, and identified that these are North Coast
right.
paths.
Okay. All right. And because they've got big earthquakes there, so that's the trick. And so underneath, but if we were to only plot 100%, right, then the black dots are pretty evenly distributed above and below. Right? Okay. Interesting.
Yeah. The issue with why we don't plot 100% or 90% is because for some of the regions, especially the Bay Area, the region itself just isn't large enough to get distances that are far enough to see an elastic effect.
That's true. That's true.
So it's a visualization issue.
Okay. This is interesting. Yeah, I like how you've got all these different types of information. That's the thing. I'm learning about that, and I'm learning about visualizing and plotting and showing data and communicating. It's important. So
yes.
Okay. Yes. And I like how your plots, your colors of the lines match the map ones, right?
Yeah.
So
always got to be consistent with your colors.
Yeah. All right.
Great. So then that leads to the model that we use, and I've already mentioned that the base ground motion model that I'm using is the BSSA 14 model.
Why did you choose that, other than it's because it's John's model?
That's the model that has, it didn't honestly matter. One follow-up study that I want to look into is doing the same study, but with the other suite of NGA-West 2 ground motion models. But it's also because John is most familiar with the BSSA 14 model.
Yeah, because it's a good point, because do you apply, and I guess it really depends on the model that you're using, because a lot of it in the directivity and issues is, where do you apply the simplification? You need to apply, you have to take it out of the model before and then putting it back in, otherwise you're double counting, right?
Yes.
And so what I would have done, because I'm always dealing with just all the ground motion models, is I would have taken that weighted average of the ground motion models and then compute that. But then there's dangers, because maybe, the Chow-Young model already accounts for this, and so you can't put the simplification, otherwise it becomes biased, right?
Exactly.
Yeah. Oh, cool. Okay.
Yeah. There have been some studies that have done the previous studies with path effects that have looked at multiple models, and they find that, for example, the ASK14 model and the BSSA14 model are pretty similar. The trends are consistent with each other. It's just the actual values that you get for attenuation is going to be a little bit different, because the source terms are different, the site terms are different. So the partitioning of the event bias and site bias from the path bias is going to be different. So it has to be done on a model by model basis.
Cool.
So also why we liked BSSA14 is because the anelastic attenuation model term, the FAA, already includes this regional adjustment, this delta C3. Previously, this was just a single value for California, but we can just readily update this delta C3 using the paths subregional method and plug it into the model. We don't need to change the model itself. It's just changing a coefficient, which is convenient because people already have codes that can implement the model. They just need to implement this one part of the model that changes this delta C3 coefficient. And so because of that, our path model actually has two terms. We have this constant adjustment, which I'll talk a little bit on in the next slide. And then in the path term, we're only modifying this delta C3. And the way that looks is the delta C3, as we've talked a bunch, just either shifts it to have a steeper slope or a less steep slope. And the constant is a small vertical shift up and down. This is more of a model, a data fitting requirement, because if we go back to this slide here, you can see that the data don't always go through zero at short distances, and we're trying to capture the slope that's right here. So it's for the purposes of model fitting, we allow this small shift up and down in the model that we ultimately fit to the data, which is this term down here with this constraint for the delta C3 star.
And what I've learned from Norm is that this shift is one thing, but in risk calculations where you're actually integrating over there, it's not just about the slope of the curve, but it's how it bends down, how it's changing. In the bottom one, you're not changing the slope of the curve. The slope is constant, while here in the upper one, you're changing the slope of the curve, and that really impacts your risk models and your sigma as well.
Exactly.
So the two things are important in how you're shifting your overall improvement from your non-ergodic to your, or from your ergodic to your non-ergodic models is these two components. So
yeah.
Cool.
So with that, just showing some coefficients now.
I love your plots. I just love your figures. It's just, I appreciate the time that you put into making them big and clear and just the right. What do you use to do these plots in the first place?
It's all Matplotlib on Python.
Yeah. I've become a fan of Plotly though. Now it's fast, especially because I can use it on JavaScript. But these are beautiful figures. So you've picked all the right fonts, and so for me, why am I dawdling on this one is it's important because it tells me that you have an understanding of what is important in the data. If you just dump the plot down, oh, here's my data. No, it's an understanding of what are the quantities in the data and what's important. And so the different colors, it's not just about making it pretty, it's you're highlighting, hey, there's a difference between them, and it's important to know which is which. So for example, here, the red one is doing something, while on the bottom one is the orange one. And so it's important to highlight the colors and what you're communicating in the different, and the fonts are big because it is the amplitudes make a difference. So to me, when I see some nice, well done plots tells me that you're trying to tell me something, not just say, hey, I got data. So I'll let you tell me something.
Thank you. So I'll let the plots tell you, but I'll narrate what they're saying.
Yeah.
So I have the equations from before shown here for the term. So we have the delta C naught R term, which is that constant, which is on the top row, and then the subregional anelastic coefficient term on the bottom row. The colors are consistent with the subregions that I defined earlier. The little x's are the values that we regress, but because it's a model, we want to smooth over those values versus period, which is shown here. Otherwise, you might get some weird artifacts in the response spectra that you get out of your model. So that's the only real purpose of smoothing. And the left shows the values, the right shows the standard error. So first, starting with the subregional constant, we see that in some areas, events might be, or the residuals are slightly positive. So the Eastern California shear zone, the values are a little strong, the amplitudes are a little stronger than what the ground motion model was predicting. In the Colorado desert, the ground motions are a little bit weaker on average than what the ground motion model was predicting. But I say this with a grain of salt because when we look at this vertical scale, it's from about negative 0.02 to 0.01 is really where the values are. These are extremely small shifts. For the constant term in the ground motion model, it's 1 to 2 orders of magnitude greater. So really the constant that this constant is adjusting is between 0.1 to like 1.5, I think, is the value. So this is a negligible shift. It doesn't affect anything. This over here, we see that we have more uncertainty at longer periods where we have less data. That's expected. But there's not really too much I want to say anymore about the constant because it doesn't have an impact. It just proves that the model that we're fitting is mostly affecting the anelastic attenuation, and it doesn't impact the other components of the ground motion model. So we're properly attributing bias to the path effects. So with the anelastic coefficients, there is a lot that can be said down here, but I just want to point out some highlights. The first thing is you'll notice everything pretty much goes to 0 at longer periods. This is because, as I've mentioned a couple times throughout the presentation, anelastic effects are essentially a friction or a damping mechanism. And at these long periods, this is high frequency. Those effects are pretty small. You don't see or it's low frequency. Because of them being low frequency, they don't have enough cycles within the ground motion to actually impact anything. So the effects go to 0. The reason why we regress non-zero values is that's what the data wants us to do. But physically, we wouldn't expect anelastic effects at long periods, which is why we constrain it to 0. And the other thing is we have some regions that have really strong trends. For example, this peachy color is the North Coast, has really high attenuation compared to the statewide average. So attenuation is a lot faster here than other parts of the state. On the other side of the spectrum is the Sierra Nevada, which is a lot lower attenuation or slower attenuation. Other parts of the state, like the Southern California and Eastern California shear zone, where NGA West 2 had a lot of data, are pretty close to 0. So this confirms that the NGA West 2 ground motion models are pretty much driven by, at least for California, are driven by the data in Southern California. They're unbiased for the Southern California regions. The other parts of the state are tend to be a little bit more negative. And this also agrees with what we saw back when I first plotted all of the data versus distance, where the trend was to go down slightly because we have where the new data is all these regions that are slightly more negative. So we see faster attenuation. I also have compared on here global values for China and Turkey in the solid black line and Japan and Italy in the dashed line. And we can see some values are similar, some values are orders of magnitude larger in absolute sense than those regional values, which again makes sense because these values are averaging over pretty large areas. So if we were to subdivide these regions, we'd probably see large scatter for China and Turkey and Japan and Italy, just like we see for California. But the average value is close to where these lines lie. And the last thing I'd like to mention is related to the uncertainty of our estimate, which you can see most of our estimates for the anelastic attenuation coefficient are pretty certain. We have pretty good confidence. The standard errors are pretty small, except for this orange region, which is northeastern California, where we didn't have a lot of data, and Colorado Desert, which also didn't have too much data. But these are still really small standard errors, so we still feel confident that the values that we have, even though they have more uncertainty than the other regions, are pretty close to what the ground truth attenuation would be for those subregions.
Okay, can you help me to understand? This is fascinating and interesting, and I like the physical explanation of the constraints that you put in. But what I'm trying to, all of a sudden now you're bringing in the standard error that we haven't really talked too much about. So I wanted to kind of picture that here in the equations, right? So, and maybe it could help, I remember talking to Greg on this, to maybe give this one color and draw an arrow so that term now goes here, right? Because that's what we're interested in, the path effect. Now you're splitting the path effect into the geometric splitting, which, and the anelastic attenuation. We're not looking at geometric spreading here. We're only looking at the anelastic attenuation. And now these are the coefficients, and now we're playing with this changes in this, right?
Yes.
Which then goes into here. And now we're looking at these two terms. What are these four different quantities? Where are these quantities in the equation? Oh, you had said that there's a constant, I guess, within here, there's a constant term plus a, oh, wait.
So the constant is up here in the
Okay, the
ground
constant is here, and it's, oh, okay. And then this thing here is the anelastic. What's the difference between? No, these are all, see, subregional anelastic, but this is subregional oh, because this is the anelastic here. So hold on, let me erase a couple of things. So this doesn't belong there. So the constant that you're plotting here, this constant here is what we see in these plots.
Yes.
Okay. And then the red is the reds that I've marked, right?
Yes. Yeah,
And
then
and maybe that could help with this figure, is to that's what I do, is to kind of color things in. And I think that, yes, now, so I think this is as far as I have made it in understanding where does the split, these two quantities go into here?
So the capital WR is the path weight in each subregion.
Okay.
So that's computed for each data. And the delta C3R is what's shown in the bottom row.
Okay.
It's the regional coefficient.
And so what's the standard error? Where does that come into play? Or is it just that comes from the statistics in computing this coefficient? Because these are regressed coefficient. And then I'm just going to put this in my pocket. This just comes from the statistics.
Exactly. It comes from the statistics to give you how confident that we are of the data. And using the standard error, we can do a statistical significance test, essentially, that confirms that these values are statistically significant. They're not just random values that you can change and they won't have effects, but they reflect the trend that the data are showing.
And so it's pretty much it's the error between the x's, or pretty much is your measurements and your smoothed.
So it's the standard error between the x's that I have shown here and the data points that were used during the regression.
And isn't that what these x's are?
These x's are the values that come out of the regression, correct?
Okay.
But the standard error is the error associated with them.
Okay. All right. I see. Okay, so the plot on the left is about the quantity, and the plot on the right is just the confidence telling me, hey, and so systematically, Northern California has error versus the model? Because you were saying that why does Northern California have more error and the Colorado Desert?
So these have more error because we have less data. So
Even
there's
still
less.
now, it's not the
Yes.
NGA West 2 to now, it's literally now. Okay.
Yeah, even with the expanded data set, there's just less data compared to the other subregions. So
Oh, because it's northeastern California.
yes, yeah, it's not the
Yeah.
North Coast. It's up where there's very few data points.
Okay. All right. I see. And then the orange one is okay. So they're both, we just don't have much data anyways. And so it'd be interesting. So maybe because this is already a log, it'd be interesting to see the comparison of the other ones. This is kind of skewing the scale as to how things change. Now yeah, okay, I see it. This is interesting. Thank you.
Of course. Yeah, even if we look at just the values that are plotted on the y-axis, they're really small.
Oh,
So
yeah.
even though this looks like it's a large value, it's still pretty small standard error. So
okay, but it makes a big difference because it's a slope, and so that has a bigger impact than the constant value above. So okay,
exactly.
cool.
So then I'd like to also just highlight the iterative procedure because I mentioned that this is an iterative step. So the first thing is that our coefficients change with each iteration. This is plotting the subregional coefficient on top, the constant on the bottom for 3 different regions. And you can see that there's pretty big changes within the first 5 iterations or so, but then they converge to pretty constant value. For where we see strong path effects, where there isn't strong path effects, the coefficients are a lot more stable because the model itself is just more stable for those regions. But this also impacts our site terms. So here is that site term, which the ground motion model is based off of essentially, is this value here. Whereas when we correct for those path effects, we're removing that path contamination. And this is a site in Northern California where we see strong path effects. And eventually we converge to, this is what we believe to be the true site term that with path effects not contaminated. And if we look at it in this sort of space where we have the site term on the bottom, within event residuals plotted with the little dots, black is the default BSSA 14 path model, the red is the updated model, the top is the standard deviation associated with essentially the site term, which is the mean value. You can see not only do we have a reduction in the uncertainty, so we're more confident that the site term is correct, which is great, but there's also a pretty big shift in our site term. This may not look like a big movement, but this is because this is in log space, that's a shift of about 0.4 or so, which is pretty big. But to highlight the effect of the path model in this, because I don't want to get down the rabbit hole of site response, if we look at the extent of the black data points, which may have path variability, we can see it's pretty wide. Whereas the extent of the red data points, we're getting closer to our average. So previously, a lot of these black data points down here are biased because of the path model in Northern California. And so by correcting that, and also a couple events were more positive, we get closer to our mean value, which is now still negative, but less negative than what was before.
And would it always be less?
It depends on what your actual site term is and what your actual path effects are. So it can be the opposite can be true where maybe you had path effects where you were more positive, so it was causing the site term to be artificially more positive. And by correcting path effects, you reduce it to be more negative or less positive.
Because that's the thing that Norm points out is that when you go to non-ergodic models, you may actually be bringing your hazard. And this is interesting also, Greg, great presentation on that, is, and by changing the constant and the slope and this and that, but that you may be getting higher values or lower values. It doesn't mean that you're just getting better, because you're always going to bring down, or you're hoping to always bring down that standard deviation.
Exactly.
And
Yeah.
that affects the slope. And okay.
Yeah.
Cool.
For the case of like a site in the Sierra Nevada, we're probably going to see that the site term goes up because the amplitudes are going to go up.
Okay. Cool.
So that's kind of some forward practical implications of path analysis.